Now let's do question number 26 on page 161. In this question, the description is given of a certain situation. There is a railroad car. So it's something like a railway wagon, let's assume. And the engine is at this end. And the mass of this railroad car is given to be capital M. Now I'm drawing this picture in the ground frame. There is a man who is situated at the other end on the wagon, so he's over here like that. His mass is small m, and this entire system is initially given to be at rest. Also given is the fact that there is no friction between the rails and the wheels, so no friction here, no friction here, which means that there is no external horizontal force acting on the system of the wagon plus the man. Now it's mentioned that this man starts walking towards the engine, and as a result the wagon or the railroad car, it recoils in the opposite direction with a speed of v, and we have to find what is the velocity with which the man is approaching the engine. In other words, the relative speed of the man with respect to the engine. So I'll just draw a diagram in the car frame. So this is with respect to the railroad car, so in which the car itself is at rest and that man is over here, and he's approaching the engine with a velocity v relative. He's moving towards the right. So that's the picture in the reference frame of the car, and we will now just use this v relative in completing our first diagram which we have drawn on the left hand side. So using our concepts of relative motion, it's pretty clear that the man tries to move towards the right with respect, he does move towards the right with respect to the car, and at the same time the car drags him back left. So his velocity in the ground frame is v relative minus this v. You can of course get the result using the vector approach also. If you set up an x-axis in that direction, first of all I'll write my equation. V man with respect to ground must be v bar man with respect to the railroad car plus velocity of the railroad car, and v man with respect to car is v relative times I cap, that you can get it from the right hand side diagram, plus the velocity of the car is minus v times I cap because it's leftward, so this turns out to be v relative minus v times I cap. So v relative minus v in the rightward direction. That's another way to get this particular velocity. Now we do want finally the value of v relative, and we can easily find it by applying momentum conservation to the system in the x direction, that is in the horizontal direction, because there is no external horizontal force acting on the system. So P initial in the x direction, I'll just remove this bar symbol, I'm treating momentum as a scalar. P initial in the x direction is equal to P final in the x direction, and this is of course 0 because everything is at rest in the beginning, and P final in the x direction. Now this equation is written in a certain reference frame, So we are writing it currently in the ground frame. So all momenta are to be calculated in the ground frame. So P final in the x direction. Let's look at the man first. Mass of the man multiplied by, let's assume that rightward is positive, so the man's velocity is v relative minus v. And under the same assumption that rightward is positive, I have to be consistent in the same equation. I write the momentum of the wagon, so that's traveling left, so minus m times v. And when I manipulate this, what do I get? mv relative minus v is equal to m times v, and that implies that v relative minus v is capital M into v upon small m, and this finally gives me an answer. V relative equals v into 1 plus capital M upon small m.